Hello everyone. I hope you all having a good day. I'm Dina Muhammad, the Future University SP Operations Head, also your session moderator today. First of all, I would like to welcome everyone for attending the session today, and I hope you all get benefit as much as you can from it. To be informed, there will be an attendance form which will be sent here in Zoom chat, so please don't forget to fill the form to get your certificate. And if you have any question, you can ask by the end of the session. And now we are very excited to welcome and introduce our instructor for today, Engineer Gustavo Gonzalez. He is an industrial engineer with an MBA in energy commerce from Texas Technology. He had been working as a professional engineer in oil and gas industry for 10 years. Throughout these years, he dealt with different production and completion practices. These practices have mainly involved finding and developing solutions and design bottom hole assemblies for severe sand, gas, and chemical issues for different artificial lift systems. While working in production discipline of the upstream oil and gas industry, he had gained the experience of leading and managing the technical sales and engineering departments at Odessa Separator. He had also been involved with SPE, currently have 6 SPE papers and 6 patents. And now let's begin our session with Engineer Gustavo.
Can you guys hear me?
I can hear you. You can share your screen now.
It shows that I'm not the host, so I'm not able to share to start my video or share the screen.
Okay, wait a minute.
Can you please try now?
Okay, now it's working.
What?
Can you guys see my screen?
Yes, we can.
Okay, give me a second. Okay, perfect. Thank you everybody for your time. Today, we're going to talk about just the first session, that is sand management for all the artificial lift system. First of all, I know we already mentioned the rules, like kind of like having some question at the end, but on the main time, if there is anyone also that have any particular question with any topic, I think maybe we can do an exception, because as soon as we keep moving forward, then maybe it's going to be a little confusion if we don't clarify the terminology or a particular question at that point. So bear with me. Anything that you guys need, just text to the group and we will try to talk about it. So they already did the introduction, but just to talk about a little bit of Odessa Separator. So we have been in business for the last 25 years. The headquarters is located in Odessa, Texas. The main company is focused in 3 different disciplines, that is sand control, gas separation, and downhole chemical treatment. One of the main focus that they ask us to talk about is sand control or sand management for all the different artificial lift systems. There is a different approach when we talk about sand control, and either that is PCP, rod pump, ESP, and basing the application, either we're dealing in a conventional or unconventional well, we maybe are going to decide different ways to deal with the sand. Either we're planning to separate that one prior to the ingestion to the pump, or either we're going to manage and giving some ability to start lifting a portion of that sand and being able to have multiple stages below that artificial lift system. Some cases like gas lift, several operators decide more to start producing the sand. We normally don't see too much damage on the gas lift valve due to sand. More in unconventional wells, we're able to use that one kind of like a flow back option. We're able to lift all the sand through the surface, but there is going to be a different problem, because that sand now has to be managed at the surface and you have to deal with that as well. So again, the first discipline is going to be sand control. And for the sand handling methods, we're going to talk about different causes or how everything starts. So we have natural factors. Either we have a consolidated degree or unconsolidated formation. Based on that, we're going to leave different type of sand. Based on the process, either I'm using some fracking operations and I'm fracking my wells, I'm going to leave maybe some frac sand combined with a small production sand. Other factor that it could induce the increase of sand production through your artificial lift system, it could be either a critical drawdown pressure. Every single time that we go deeper and we try to increase the drawdown, we maybe are pulling more fluid, but at the same time, we're pulling sand that is going through. Some frac job that maybe you get hit by a frac well, and now this used to be maybe an old rod pump well, and you maybe didn't face with any sand, but sooner or later, now you start producing a ton of sand because you see some communication or colingo in those particular formation, and now you're lifting that sand. Fluid velocity that is passing through, and water floating based on the application that we're dealing. So I kind of like to show this picture because it gives us kind of like the view that we use on the conventional reservoir and the unconventional reservoir and what we try to accomplish with each of those. So a regular conventional well, we kind of like know where the oil is located. So we either drill vertical or incline based on each particular case, and we try to just attack that particular area, and that's where we perforate, and that's where we start producing the liquid, just for that zone, either 100 feet, 500 feet, 1,000 feet. On an unconventional well, we kind of like go with a different approach. We try to keep our wells vertical the first 8,000, 5,000, or 10,000 feet based on case by case, and we either go 1 mile, 2 miles on the horizontal section, so we're able to have better communication and try to keep all our production area right straight on the middle of that reservoir. So hopefully we get a better inflow, we're able to lift more fluid, and maybe use a different method to approach that particular. So again, conventional wells is more wells drilled in deposit with a high permeability, and unconventional wells is more reservoir with poor flow properties and low permeability, high density fluid. And in those cases, that's where we use that frac sand just to go over there and stimulate more that area and being able to create those mini fractures internally and open that porosity and being able to lift more fluid. So this is kind of like a view that we like to show on the conventional versus an unconventional wells, how the sand behave when we're lifting the sand. So typical approach, if we're dealing with a conventional well, we got multiple options to avoid those issues. Either we set up our pump above the perforations. So in that case, we are able just to deal with the gas, but the solid will try to fall down into the rat hole, because if we try to put our pump right below the last perforation, if we have some rat hole, at that case, we can maybe face some sand into our system. There are applications that maybe we're not able to deal with that, but what we normally see on the initial stage is a plastic hole deformation. We see a big peak when we're lifting all that sand that is coming from the reservoir until a point that we start to create some stabilization and we decline the reservoir pressure. So the amount of sand that is being produced is going to be less. On an unconventional well, we normally see different type of profiles. So we kind of like go back and we see that initial peak, and either we have some enough bottom hole pressure that we can get some flow back, and hopefully if that's the case, and that particular reservoir that you're producing, that area is keeping enough bottom hole pressure, you can maybe clean or leave around 30 to 40% of the sand that you're dealing. If you don't have enough bottom hole pressure, what you have to do now, either you have to take a decision to go with an ESP or gas lift and try to set my artificial lift system to handle the sand and being able to produce the sand because my bottom hole pressure was not enough. But we're going to get that peak. We try to see some stabilization, but based on the areas, we have multiple wells that has been fracked around, and we can get some small frack hit, and that's where we see all those curves, and maybe one well that you already depleted like 3 years ago, and it was already stabilized. Now you get that peak again, and the amount of sand that you start to produce increase, and you're kind of like in that rolling coaster over and over and over, and it's based on the development area and the communication that you maybe are facing in that particular field. So how we get that communication, or what we normally see those in unconventional wells. So we talk about based on the field spacing and where exactly I start to produce, either I'm dealing, and I give you kind of like an example, either I'm in both springs, Wolfgang A1, Wolfgang A2, Wolfgang B, and based on the trajectory that I have for my well and the density that I have on the intervals that I'm spacing every single of those. So in one point, either if there is so many holes or so many wells that you get around, you can face some communication between those two due to the interface and the density that you're getting. Like the space between one sump to the other one is just 150 feet. Some cases you can get 330 feet. So based on that, you're going to see some communication. And at that point, you're changing that particular reservoir, you're changing the pressure, and that's what you go and you see maybe an increase in production in some cases, but an increase in sand production as well. So either you're changing that stability that you already have previously, and now your reservoir start to behaving a little bit different until you're able to pass through that phase and now control this. But again, it could be also that you get a parent well and you get a child well, and now you see that impact of that communication between those two wells, and at that point, that's where you're getting all the changes, either in gas or you're getting the changes based on the sand that now you start lifting. All of those is kind of like a constant, getting, oh, that's different. In some of those cases, we're going to see different behaviors. One of the best things that I like to show always is more, this is a beautiful picture about the Permian Basin and the number of holes or wells that we get around and the spacing between one of those two. So you can see we got several areas that is actually has been developed really well, and the number of wells right next to each other is increasing. And at that point, we're facing now communication problems on the future, either one area, one particular path that maybe I developed like a year ago, and now I'm facing a new development, but I see some communication between those two based on what exactly my lateral section is going through. So just keep that one in mind, because those reservoir condition, it could change after time. That's what is always a good idea. Design your artificial lift system to be able to handle that sand, because you cannot disappear the sand that you either use to frack your well, or that is your formation sand that is coming through. Either you design your pump to be able to handle a portion of the solids, or you find accessories or alternatives that it can help you to handle that and being able to improve your runtime and decrease the damage in the pumps. So let me try to put this video. I hope everyone is able to hear the video and watch it.
Geologists have known for years that substantial deposits of oil and natural gas are trapped in deep shale formations. These shale reservoirs were created tens of millions of years ago. Around the world today, with modern horizontal drilling techniques and hydraulic fracturing, the trapped oil and natural gas in these shale reservoirs is being safely and efficiently produced, gathered, and distributed to customers. Let's look at the drilling and completion process of a typical oil and natural gas well. Shale reservoirs are usually 1 mile or more below the surface, well below any underground source of drinking water, which is typically no more than 300 to 1,000 feet below the surface. Additionally, steel pipes, called casing, cemented in place, provide a multi-layered barrier to protect freshwater aquifers. During the past 60 years, the oil and gas industry has conducted fracture stimulations in over 1 million wells worldwide. The initial steps are the same as for any conventional well. A hole is drilled straight down using freshwater-based fluids, which cools the drill bit, carries the rock cuttings back to the surface, and stabilizes the wall of the wellbore. Once the hole extends below the deepest freshwater aquifer, the drill pipe is removed and replaced with steel pipe, called surface casing. Next, cement is pumped down the casing. When it reaches the bottom, it is pumped down and then back up between the casing and the borehole wall, creating an impermeable additional protective barrier between the wellbore and any freshwater sources. In some cases, depending on the geology of the area and the depth of the well, additional casing sections may be run and, like surface casing, are then cemented in place to ensure no movement of fluids or gas between those layers and the groundwater sources. What makes drilling for hydrocarbons in a shale formation unique is the necessity to drill horizontally. Vertical drilling continues to a depth called the kickoff point. This is where the wellbore begins curving to become horizontal. One of the advantages of horizontal drilling is that it's possible to drill several wells from only one drilling pad, minimizing the impact to the surface environment. When the targeted distance is reached, the drill pipe is removed.
Oh, my bad.
An additional steel casing is inserted through the full length of the wellbore. Once again, the casing is cemented in place. For some horizontal developments, new technology in the form of sliding sleeves and mechanical isolation devices replace cement in the creation of isolations along the wellbore. Once the drilling is finished and the final casing has been installed, the drilling rig is removed and preparations are made for the next steps, well completion. The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins. Initially water and then natural gas or oil flows into the horizontal casing and up the wellbore. In the course of initial production of the well, approximately 15 to 50% of the fracturing fluid is recovered. This fluid is either recycled to be used on other fracturing operations or safely disposed of according to government regulations. The whole process of developing a well typically takes from 3 to 5 months, a few weeks to prepare the site, 4 to 6 weeks to drill the well, and then 1 to 3 months of completion activities, which includes 1 to 7 days of stimulation. But this 3 to 5 month investment can result in a well that will produce oil or natural gas for 20 to 40 years or more. When all of the oil or natural gas that can be recovered economically from a reservoir has been produced, work begins to return the land to the way it was before, 3 to 6 feet below ground level. All surface equipment will be removed.
Okay, I hope everyone was able to hear the video without any problem and see what was happening on the screen. One of the main takeaway is kind of like the amount of sand that we use to frack these wells. And that's something that I always try to bring up so we can put some numbers behind it. So normally the timing for fracking the well, it will vary. It will change based on formations. Each country is going to be different based on the regulations, but kind of like base analogy for this particular case that we try to do around 62 stages. We normally for make or to frac 10,340 feet of the lateral section, they use around 21 million pounds of sand. So if you try to extrapolate the numbers, so you're using a lot of sand as you were able to watch on the video. What we tried to accomplish with that was generate enough permeability. So as soon as we frac each of our layers or sections that we get over there on the stage, what we want to do is cause enough permeability so we're able to increase the flow and allow that pressure to release through these perforations. And now we're on the middle of that reservoir. So we're able to capture all the pressure that it tried to release from the formation, being able to pull all the fluid, which mean oil, gas, and water. But at the same time, due to those pressures, some of the sand that we use to frac these stages is going to come back. Not 100% will remain in the reservoir. But now what do? Either we have enough bottom hole pressure from the beginning to allow this well to flow, or we have to design something that it can allow us to deal with the sand. So always keep in mind what's going to happen with the rest of sand that is coming back. It's 30% is the amount that we're able to flow back. So I kind of use this picture just to show us all the amount of sand that we're using. And let's take the numbers to do an easy calculation. If we take just that sand that is coming from the flow back, that 30%, it will be kind of like equal to 6.3 million pounds of sand. And if you take that number and now divide it in how many joints I need to store 6.3 million pounds of sand, is going to be equal to 2,715 mud joints. So if you now convert this of how many feet, that is going to be equal to 84,165 feet. So again, just to give you a number, if we have a well that is kind of like 8,000 to 9,000 feet, we can fill almost 8 wells on the entire curing section, just full with sand on the initial flow back. So we always deal with high amount of sand. Now the key factor is how do we handle that when it's coming back? Our artificial lift system is designed to handle with the sand. The problem becomes is more when we're getting all the sand at once and we're not able to dosify or regulate how much sand we're giving the ESP to produce. So now the ratio between fluid and sand is going to be different, and sometimes you cause too much erosion through the system, and that's what you cause some of the issues. So again, this one is kind of like just to show the production profile that we're getting on those new wells. So a conventional well, brand new well, we start putting online, we get some of the flow back. We're reaching kind of like 5,000, 6,000 barrels per day. And at that point, it starts slowly decline because I go back and my pressure is decreasing. And either when I'm reaching either the 1,000 barrels per day or my pressure is coming too low, I stop that flow back and I decide just to go with my artificial lift system, either my ESP or my rod pump or my gas lift, excuse me. And again, it will base or it will change based in some areas. I know like in the Bakken or North Dakota, sometimes they go straight with rod pump. But again, it's no 8,000 feet. We're talking about shallow wells, like it's maybe 3,000 feet. Just the unconventional section is really short. So it will vary in base in case by case. This is a pattern well profile. And in this case, it's kind of like unusual. Instead of going, reach the peak and come back, in this case, we went back, we kind of like reached the peak and it's still increasing, it's still rising. And it's because I start seeing some communication on this particular well. And now the amount of sand that are able to flow back is actually higher than a traditional well. So again, each well is going to behave different based on the communication and the number of paths that you have in each area. So for the sand management, there is always, like we discussed from the beginning, there is always 3 different areas where I can deal with this. Either I deal at the surface, and you can face several consequences. You can damage your valve, the instrument. You can fill out the separators, or you have to use some of the desander or sand traps that you use at the surface, and you have to have more than 2 or 3 communicating together to be able to handle that high volume that is passing through. Sometimes you can wear those vessels, and due to the amount of pressure and sand that is passing through, you can start seeing some of the issues in the system. Also, I think someone is raising the hand. Let me see if I can. I don't know if someone has a question, but I have been seeing someone is raising the hand. I don't know if any of you guys that are controlling this can help me to see someone have a question, or it's just kind of like something that is going in and out when people is logging.
If there is anybody need to ask a question, he can raise a hand, and we can let him ask the question.
I saw that there has been like 2 or 3 people raising the hand, but I don't know is that actually that they have a question or not. I don't know if you guys can control that part, but I'm getting the notification. I just don't know how to give an access. Would you like me to continue, or just wait a little bit until you guys can figure out who actually has a question?
They say all is clear, so continue, please.
Okay, so as we were mentioned before, at the surface, so it's more the malfunction or damage that I can get on the vessels or all my valve or surface separator that I can fill those out. So I need to have constant improvement, and I need to have people 24/7 to be able to help me to control the sand at the surface. Now in the well or the reservoir, is more on the well is what's going to happen with my artificial lift system. Either I get some stock lifting equipment, either I get all the stages from my ESP totally destroyed, or if I'm dealing with gas lift, now I can see some of the valves just being damaged, and I start losing some of that efficiency of my system. Erosion and abrasion is something that actually can affect me moving forward. And again, we're pumping a lot of frac sand, as we discussed, and some formation sand that we're producing. So it's going to be high volume passing through the equipment that it can cause that erosion moving forward. And the access and the restraint section that I can get on my reservoir, sometimes due to the volume of sand that is lifting through, I can start, if I'm dealing with a conventional well, I can start building sand on the rat hole, and it's slowly still raising up, and I can feel just 1,000 feet, 800 feet, or 2,000 feet, and I can plug those out. Now I get my tube in stock with my pump, and I need to go back and just doing a clean out and being able to leave everything. And you know, that's kind of like the nature that I'm facing. On the unconventional wells, I can see the same phenomenon. A lot of sand could be start building in the heel, or start building on the lateral section, and I can see that my pressure is slowly start changing, and the amount of fluid is decreasing, because now I have a restriction point on my lateral. So some of those is going to cause poor efficiency, and at that point I need to take some actions, either pull the well or wait until it fails and go back and do a clean out. So like we mentioned before, there are different approaches that I can use with my artificial lift system. If we're talking about ESPs, there are different metallurgics that I can use, or special pumps that are designed to handle some of that sand. For the sand control method, there is different approaches as well, either based on the content, based on the areas. Either you can see some gravel pack, you can see some premium screen, some sand screen, some desanders. It's more how do we want to face with this, and every single approach has some pros and has some cons. So it's more we need to design the right based on the target of the philosophy that we have as an operator. If I'm planning to keep this well with a higher runtime, and I have this pond and my depletion curve is not that high, and I'm regulating more that inflow, you maybe can accomplish a higher runtime. But I see on the other hand that we maybe go with an initial big pump, and in less than a year, and now that pump is oversized and it start failing due just to overheat because now it's gas racing up and my well is just down every single 20 minutes or every hour. So that's kind of like the balance that us as a production engineer, we have to go back and design this and being able to take a better approach. Surface control is going to be the use of the cyclones, how we're transporting that sand at the surface and disposal, everything. And the production rate restriction is more how we also are going to operate as well. And maybe we go back and we decrease the drawdown, and we reduce in this case the frequency and to control more the forces of the drawdown that I'm creating in my formation and how much sand we're pulling. Sometimes could be just based on where your perforations are located, I can raise up my pump to be able to start producing enough. I have enough submergency. I can maybe stop dealing with solids at that point and just allowing those to fill that bottom hole section until a point that is economical for me to go back pull the system and do a clean out and come back again with a new design. So this is one of the pictures that I like to show, and it's more how the sand actually behave than oil. So when we're talking about formation sand or frac sand, this is what we're actually are imagining. We always imagine one particle at a time. If someone is talking about 20-40 frac sand or 100 mesh, we always imagine just one particle, and how actually it looks like each particle is like this. But this is sand that has been dry. This is either frac sand that hasn't been crushed. On reality, what we're going to see in any well is more this. Is sand that has been compacted, is sand that has been agglutinated due to the viscosity of the oil, due to the content of water. You're going to see some agglutination or some chunks that are passing through your pump. So when you have any artificial lift system, the way that the sand behaves is not just one particle at a time anymore. It's just getting this huge amount of sand or paste or batches just going through my pump, and that's what is going to cause the plugging effect, or that's what is going to stick my plunger. So that's in that case, I need to understand how or what I can do to start breaking or regulating this amount of sand before it goes through my pump. So I like to show also this picture so it gives you guys a better understanding of the problematic and actually what I was mentioning before, how the sand behave and what I'm going to see. So this is kind of like the stages of my ESPs. It's totally plugged with sand. I mean, when I'm lifting that frac sand and based either in number of shoot downs that I get on my wells or the inflow that I was having and the drawdown, you're going to see that you slowly start plugging your stages to the point that the ratio of sand was more than the ratio of liquid. And you can see that it's just plugging 100% your system. And the amount of erosion that it can cause to your pump is going to be high. So another thing is actually plugging, like the ESPs, by default, they come with this screen as an intake. So if you do the calculation of how much fluid you're actually flowing through, some cases, the base approach, due to the high delta P that you're generating over this intake, is to actually remove this small screen section that is actually 1 foot long. So you can actually cut that out and remove it. You can ask your ESP supplier. At that point, you will expose 3 different holes, and you would allow to increase more the open area. And again, it goes back based on how much solid and how much pressure drop and which stage of your pump you are. Either you're in a brand new well that you're lifting 5,000, or you're in a well that you're just producing 350 barrels and it's not an unconventional and it's either a water flowing well. So again, this screen is normally designed for more lower rates and wells that you don't have high scale precipitation or iron sulfide. But when you're dealing with new wells, just to be more proactive, we always recommend to remove that out, increase the open area, reduce the pressure drop, and being able to have a better ingestion of sand. Because this open area is not going to be enough. At that point, you can face some plugging, as you're able to see right now. On rod pump, what it normally happens is the same phenomenon. I get a work project. The amount of sand that is passing through my standing valve, maybe it was okay and I'm able to lift that up and without sticking my standing valve. But now that sand has to pass between my plunger and my barrel. And after I lifting some of the sand per stroke, some is coming back. And now it's coming around my plunger and barrel. And now this is what I'm causing. This is what I see, that friction. And that's what we normally see, a lot of buckling that is happening on my rods, what it cause an issue on my tubing. And at the same time, I can see a lot of friction on my upstroke and downstroke, and it's due to the amount of sand that is now between my plunger and my barrel, and that displacement is now generating more friction and causing some inefficiency every single time that I'm lifting. And again, sometimes becomes the point that the ratio, the volume of sand that is passing through my artificial lift system, in this case, either my standing valve, is too high and it's too severe, because either I got a high sand batch passing through and it just get plugged. So again, that's why choosing the right method to complement your design for your rod pump or ESP is going to be a key factor to increase the runtime. Some areas we use PCPs either after the second installation or after the first installation or in the first installation. And you know, PCPs are normally designed to handle sand, and they do an amazing job. You actually can lift more than 30 to 40% of the rate of sand compared with a rod pump. But it becomes to the point that that volume is now too high and too severe, and the damage that I'm causing to my stator and to my elastomer is going to be severe. And either I can start losing my efficiency due to the crushing that I'm seeing between this elastomer, or if I'm dealing with any gas as well, it's going to start swelling the elastomer. And when I have the combination of sand and gas for my PCP, those are two that is kind of like affecting the other one. So on sand, I'm able to leave that sand without no limitation, but now that gas is affecting my elastomer, is creating some swelling, and now I'm creating more friction between those two to the point that I can plug the system and cause another failure. So one of our approaches, instead of getting this chunk of sand going through your pump, there are multiple ways that we can regulate and we can control that volume that is passing through either per stroke or either every single minute that is going through your system. So what we normally do, there is different approaches. Again, it goes back based on the artificial lift. In the case of ESP, as you guys are aware, the intake of the ESP is on the side, as we saw in the previous picture. So in that case, to be able to regulate the amount of sand that you pass through, I have just three different alternatives. The first one, either I go back and below the sensor, I put my sand control system, either a desander, either sand screens, either completion screens, whatever we already analyze and we consider is going to be the best approach for this particular well. But there is a limitation. If I go with a cut style packer just to isolate my intake or my perforations, the perforation has to be below the cut packer. So I can keep my flow path, fluid is coming from the perforations, goes up, goes through the screens, goes through the desander, pass through the equipment and exit out below the sensor. And now the fluid with less volume of sand, it will go around the ESP and it will go through the intake. So that will be the isolation method that I can use this. In case that you're still keeping your perforations underneath it, and either you have a lot of issues with those cut packers because it's wearing off, or you are putting too much weight below your ESP and you want to avoid any risk of actually pulling your ESP just to one side and facing too many broken shafts, the other approach that you can use is either go back set a mechanical packer or rotational packer, you have your sand control system underneath it, similar like the previous one, either desander, either it's green, it goes back to the same approach, gravel pack, whatever you want to do. But the perforation has to be underneath that packer. So fluid can go through your sand control method, goes up, you have to use an on-off tool, so you can go back, set the packer, remove the tubing, pull it back, and go back with my ESP. But at that case, I keep those two sections separate. So you can pull that ESP back at any time without pulling the sand control management that you have underneath it. Or if you're doing an amazing job and you're able to control this without affecting the inflow, you can maybe go back, and after you deplete this well, you can go back with the rod pump and you already have the sand control system underneath it. Someone has a question? I believe.
Mr.
Omar?
Gustavo, can I ask you a question?
Yes, sir.
How can I prevent the sand from entering the downhole pump?
So that's what I was saying on this one. You have to select the right method based on your perforation. So the way that you can control that out is you have to isolate that. In this case, if that is an ESP, that's what I use this method with the cut packer. So the sand has to go to the sand screen, and at that point, you are controlling the amount of sand that is going through or is passing through. Or if you put a combination with a desander underneath it, you are sending a portion of that sand through the tailpipe. But to be 100% honest, you cannot separate or filter 100% of the sand. If you do that, you're going to plug the entire system and you're going to fail. So the right measurement to do it is actually being able to produce a portion of the sand. So you're controlling this, and instead of getting, let's try to put everything in number, instead of getting, let's say 300 pounds at the same time, you maybe are getting just 5 pounds of sand with every single barrel that you're producing per minute, or less than that. So you cannot disappear the sand. The only thing that you're doing is delaying that process, regulating, and provide the right amount of sand that goes through your pump. But normally you go with your ESP and it's exposed. It doesn't have any sand control underneath it. That's the only 3 different ways. Either you put a shroud because the perforation are now above, and this is how you control the same thing. I don't know if that answered your question in particular. There is always resin coating, different approaches that you can do if you want to pump something to your reservoir to hold portion of the sand. But again, in one point, those are going to be inefficient again, and you're dealing with that sand because that sand has to come back.
Thank you, Mr. Gustavo. It's clear now.
So just to recap again, either I go with a cup style packer, you don't have to activate this packer. Either you go with a mechanical packer, you have to activate this packer and you have to rotate. So that's why it's going to be separated from your packer, so you don't twist that cable, and you have to do 2 different runs. Or if the perforations are above and below your ESP, we have to encapsulate that ESP, and we do the sand control method underneath it. And we're going to talk about better of each method and how exactly it works. But just to give you an idea, on ESP, those are the 3 different ways because your intake is around. On rod pump, you can connect this just below the setting nipple, and that's it. You don't face any issue. In PCP, the same thing. You can connect that one below the last joint of the tubing because this is your intake. Your intake is always coming from the bottom. ESP, your intake comes around the pump. So that's why we have to isolate it a little bit different. So there are different types of sand and how that sand can affect the system. So in occasions, and I'm giving you kind of like a wellbore on the left, so we can go from the top down. So let's say you're dealing with a lot of sand. And what we're giving you over here is kind of like the option that we discussed. Either we have the cut packer, so perforations are underneath it, fluid pass around, go through my sand control method, flow up, exit out around the ESP, and kind of like go through my pump, and now able to deal with that sand. But like we mentioned before, we cannot filter 100% of that sand. We need to control that ratio. But in cases that either you have some electricity issues in your well or your field and your ESP goes down constantly, what is going to happen, whatever the sand that you were producing through your tubing is going to start to fall down. And that sand could be just start packing above your discharge of the pump. So there are different approaches that people have used in the past. Either they go back and they put like a check valve just above the discharge to be able to control that sand that is falling back. And they want to have that head kind of like free. So when I restart my pump, I'm able to use that pressure to open that check valve and being able to flush off the sand again through the surface. The problem becomes when you're dealing with high sand volumes, now you get either 3-4 joints above the check valve and your discharge pressure is not high enough that you're not able to overcome that hydrostatic pressure plus the weight of sand that is above it, and you start pulling the well just because of that problem. So this approach or this particular product is able just to regulate the amount of sand that is coming back. So the sand leaf is used above the ESP, and the approach for this one is kind of like have like a unique angle of the screen. And what it's going to do when you're getting any shutdown, you're using your hydrostatic tubing column or the head that you get on your tubing, because your ESP is down, you're able to back spin your system. So you're regulating how much sand is going to go through the pump and being able to flush that out. So again, you always can deal with that sand again because that sand already came from the wellbore and it came through the pump. Now you're able to push that one back, but the key behind everything is instead of getting everything at once, we're regulating how much sand is going to go back through the pump. And that's why this tool is designed. It's not to pack the sand around this equipment and hold it above your ESP. This tool is designed is just to regulate how much sand you're able to produce back when you're back spinning and being able to liberate some of the head that you're building above the discharge of the ESP. So again, this is not a sand, it's not a filter. What you're using is more an approach to manage the sand when you have the shutdowns or when you're facing that flow back that is coming in through your pump. So this is how you can manage above the ESP. But if you have high sand volume, that erosion already went through the pump. So this is just an alternative solution that you use above the discharge. But if we're coming now underneath it, there is different methods that I can use. I'm just going to show you a quick video how the sand lift work. So it kind of like allow us to get a better understanding of where do I need to use it and what is the main concept.
One of the primary issues in artificial lift is handling the solids during production. During a shutdown, sand in the production stream falls back into the pump and creates a solid plug in the pump. This can cause a failure when turned back on. This failure is costly to operators. Operators need a solution to be able to backspin the pump and treat through the pump with chemicals from the surface. The purpose of the sand lift is not to stop sand above the pump, but to regulate the rate of sand going back into the pump when the pump is shut down, reducing plugging and allowing for chemical treatment from the surface through the pump. SP pump turns on the differential pressure created by the pump, pushes the dart sand breaker off of the open landing pad to the top position. Fluid and entrained solids flow through the tubular ports in one flow path to the surface. When the pump is turned off, the dart sand breaker falls back to the open landing pad. Fluid and entrained solids begin to flow back through the tubular ports following the same path. The dart sand breaker and tubular ports regulate the rate of sand that comes back through the pump. Because the sand lift has no seal, it provides the operator with the ability to chemically treat through the pump from the surface and use the backspin to clear obstructions from the pump.
As we mentioned, this is how we're able to actually allow that regulation portion where I'm flowing through to still have enough open area and there is no seal. So this is what you're able to use, that either flushing operation or tubing head to allow that ESP to handle that sand back.
When the ESP pump is turned back on, the centrifugal force of the ESP creates turbulence, which lifts the fluid and entrained solids up through the tubular port to the surface.
So just to give you an idea, this is kind of like the angle of the screen. So it's inclined and this is how we're able to regulate. So just want to give you like a better picture of that. This is what we have internally. So this tool, you have the housing that is with a high erosion resistant material. So it's boronized and you're able to actually hold all that erosion when you're restarting your pump. But it's more, again, like we mentioned before, is how you're able just to regulate that sand that is coming back. And you have the ability to open and disassemble the tool every single time that you're facing any tear down or you're pulling the well. So you have the option to remove all the inner components and being able to get samples, flush everything. Normally, this tool, due to the regulation factor, every single time that you're pulling it, is going to give you the option to refurbish, because what we want to do in this is kind of inspect all the erosion. Like as you can see over here, we're just pulling everything on the internal housing, so the screen comes clean, and we're able just to readdress or just replace what is needed and being able to come back and reuse it back into your well. Now to the second point, on the same BHA, we're going to use two different centralizers. And the main reason of those centralizers is we always talk about when we're designing our ESPs, we don't want to be in a high dotlet or high inclination. So what we want to do is give enough flexibility to the ESP that whatever equipment we have down below the sensor is not going to pull your ESP just to one side and generate some buckling that it could on the future affect your ESP, because you're now pulling that shaft just to one side, and the amount of vibration that we're seeing through your pump when you're dealing with a lot of solid, it could cause some future damage. So the centralizer is just to help and keep everything centralized. At the same time, it's going to kind of like a shock absorber, is going to absorb some of that vibration that it was coming through and being able to have those ESP on the ground for a long period of time. That's why it's so critical to analyze the survey. So we always analyze kind of like the 3D view, where is actually the sensor and how much tailpipe we're putting underneath it. Because that's something that we always come back and we discuss with the operators and the ESP companies. We may be putting our ESP on the right inclination and the right dotlet, but we have to analyze the integral system that we're designing to control that sand. And what I mean with that, either if you go with a regular desander, your sensor and ESP could be less than 2 degrees of inclination, and the dotlet could be 0.2. But what you're going to see is now the bull plug or the amount of tailpipe that you're putting below the desander. Now you're in an inclination around 27 and your dotlet is around 10.3. So at that point, that's what you can face some issues, because you're actually bending that system and pulling everything out. For this particular case, you have to have a slotted outlet. That is where the fluid is exiting out, and you're able to actually do the sand management underneath it and have a fluid with less volume of sand passing through, and now you're able to produce that one through your ESP without causing enough damage. So the key point is always design with enough open area. How we do that, we analyze the number of slots versus the total fluid that you're lifting. Traditional 2.78 tubing, your regular open area is around 4.68. In this case, we always try to go at least 2 to 3 times more open area to avoid any plugging or avoid any issue. And the cut packet is just to be able to isolate the system. And the reason that we go one cup facing up and another one facing down is actually to use that hydrostatic head that we have around it, so we can squeeze this elastomer and create a temporal seal. The same thing with the second elastomer that is underneath it. We use the bottom pressure to improve this out and kind of like generate the seal that we need to be able to control the sand. Once again, you don't have to activate these type of packers. The OD of the elastomer is actually close to the drift of the casing. There is several type of elastomers, ones that they have wire on the inside. This one is 100% elastomer, so it gives you more flexibility to create more expansion when it's needed. And when you pull the weld, you just pull with the tubing and this comes out. You can always analyze based the type of inhibitor that you're pumping or gases that you're producing. So, you know, choosing the right elastomer type is another vital factor that we need to keep in consideration based on the parts per million that we're seeing of H2S. So we maybe want to go with Aflax. Based on the bottom hole temperature, we want to go with a Byton, or based on the type of inhibitor that you are injecting, either a lot of amines, you can go with HMBR or HSN, and there is different hardness. Again, that's where you need to go back and rely on your service company to be able to design the right appropriate method for this. Or you can do a triple seal in case that you're seeing too much gas, CO2 or H2S, that it can start swelling the elastomer. This one will stop that, and you will create a better seal in the middle to overcome this. Also, when you milligrams per liter, if you're dealing with more than 200, it's better to go with a triple seal to guarantee that you're not bypassing the system and not forcing the fluid with the sand to go through this. So again, in this case, what you want to do is there is always a concern of the screen. Like either the screens can plug, either you can see a lot of issues. I think there is some questions. There is two participants that raised their hand.
Yes, can you hear me?
Yes, I can.
Hello, Gustavo. Thank you so much for this presentation. I do have a question about a previous slide. You mentioned that there are different methods that can be helpful to manage the production of sand. And one of them was like an special pumps, and the other one, the tubing screens that you already show us. So I would like to know if is there, like, which of these two options that I mentioned, which one is more efficient, less expensive, and more popular? Like, which one is the favorite that the operator uses? Do they prefer to buy a special pump that can handle the sand, or do we use both of them, or the tubing screen and also the pump? Which one do you think? Do you have an idea in the oil and gas market which one is more popular and more efficient if we compare these two methods?
Yes, so if I get your question correct, it's more when do we use an special pump and when do we use something underneath it. So the way that we have seen this, there is not like a silver bullet that could be or has been standardized in the tar field and is going to work, but having enough knowledge from the field that you guys are developing or planning to start drilling, and after that go with any of these type of artificial lift system, you always know kind of like how much H2S either you're going to spend. There is always a gamble. You know, the reservoir team and everybody tries to do an amazing job for trying to provide enough information and enough data to analyze the fluid properties that we're going to face. The majority of the people, again, we try to go with either a tungsten or some ceramic, or I have been seeing some people do some zinc coating and stainless steel coating on the outside. And it goes based on some people it may be facing with sand, but also H2S. And now they start seeing hole in the housings. So there is not a right or wrong answer. What I will suggest, you always, based on the history that you're facing, you try to tell but you have to tell your ESP provider, this is the problem that I'm facing. They're going to give you multiple scenarios. So we always work on the way we try to, based on the volume of sand that they see in the flow back, we kind of like go back and we tell them, this is the ratio that we're kind of like producing in this field or these particular wells. And you're kind of like given like an estimate of sand that the ESP or that is going to start lifting and facing. I was going just to give an example, like there was one well that we did a couple of weeks ago that we were expecting 120 pounds at the surface, and this well came back and the bottom hole pressure increased, total fluid production actually went up like 40% more, and now the sand rate of course increased, and now we're facing 288 pounds of sand at the surface. So imagine how much sand is passing through the ESP. We went with a tungsten shaft. We designed the pump to be able to have a stronger system that it can handle that erosion and it can handle that compactation of sand and that crushing that you're going to see for the stages. But again, we come back now to other fields and really you have enough flow back that you're able just to put in a standard pump and you can achieve a decent 1 year runtime. Again, it's kind of like a little bit different and difficult to say this is the well. If we go overseas, I has been seen again, huge pump that has been coated on the outside and productions are a little more steady. So you go for a well that is producing 7,000 barrels per day and you're keeping that one like that. And but because the amount of fluid compared and the ratio of fluid compared with sand is higher, so you're able to lift ton of sand, and 280 pounds is nothing for those pumps. So again, it goes back, it's based on the ratio and the proportion of sand that you're getting through. I hope that answered your question, but it's really difficult, kind of like just to give you a better answer, the way to go that I have been seeing people using, they just go back and they say, you know, I get sand, I put a desander. Isn't seeing so much broken shaft, I kind of like go with an upgraded version and I go with tungsten shaft. So that's kind of like the first reaction or approaches that they try to do as soon as they're dealing with sand volume. If they really want to focus in handle the sand, method like completion screen or sand screens could be applicable, but again, it's more looking for a long term, and it's a well that you're not pulling in 3 months, 4 months. We're looking for something that it can give us at least 1 year because the investment that you're doing is significant. Is there any other question? Or I saw 2 people raise their hand. So there is no more question?
I think there is no more questions. Please, if you could continue.
So going back, it's worth selecting the sand screen as a method, as I mentioned previously, is going to be that concern always, you know, some filters or the screens plug-in effect. And yes, that's possible. That could happen. Probability to happen is really high. Is they don't do a good job selecting that opening of the screen and understand how the sand is actually behaving in your well. So this tool, this bypass valve, is actually designed to give that additional alternative in case that the sand screen is plugged. So you're opening a valve system that you have above it, and you're opening this spring is because you're overcoming the 33 psi that the spring is set. So what we're showing over here is, let's say the main screen is just plugged. Now you open that, due to the delta P, you open that you compress that spring and you open that secondary intake, and it will guarantee that your ESP or your PCP never operate dry. You always operate with enough fluid without causing any restriction through the flow and without causing any damage through the system. So normally either you can do a wider and bigger opening on the bypass, or you can go with a slotted sub and you can still have that bypass option. So this is just different alternatives that it could be designed based on the well-to-well application. One of the things to go back with the main screen as the primary intake, there are different slot sizes, and kind of like the common question that we always get from people is either I'm dealing with 100 mesh or 4060 or 4070, and they say, give me the tightest screen that you guys have. If we do that, as we mentioned previously, due to the volume, we're going to plug the screen because as we saw in the photos at the initial, the sand is more like a paste. So based on those cases, we try to talk with people and talk about what about is we're able to just regulate instead of filter everything at once. I know your artificial lift system can lift the sand, but instead of giving just the 3 holes that we mentioned at the beginning that the ESP has as an intake, instead of having just 3 doors, we're going to give you 1,000 doors that you're able to open and regulate how much sand can actually access through. So the way that we do that with those sand screen, we open that gap, let's say like 12 or 15,000 of the inch. And when that paste or that sand that has been agglutinated, that increase the size due to the agglutination is passing through, what we're doing is more like a baffle effect. And you know, the sand is not falling down whole, because it still be lighter enough that some portion is going to be suspended with the fluid, so another one is going to be just agglutinated. And you're going to see more the sand passing through the screen and heating that screen over and over and over until you're breaking and losing that agglutination and you allow those particles to flow through. At that point, you're not plugging your screen, you're just regulating how much sand can actually pass through. And you can do either just one stage and lift this portion of the sand, or if actually the well produces a lot of sand, you can add a desander underneath it. And at that point, you have 2 stages. And we're going to talk about that with a little more details. But again, main thing for the sand screen, you have to analyze and you need to know the particle size distribution and how the sand is going to behave. When you talk about this, don't think just like pure fluid and just sand. You always need to analyze the scale tendency, the pressure drop that goes through the screen. Always when you design the sand screens, try to have the lowest pressure drop that is possible and enough open area that you're able to overcome this chemical limitation, because any well is perfect or any well is just sand. You always get combination between scale, iron sulfide, some few you will get some paraffin. So all of that is coming through the screen and is going to be the first entry point through the fluid, and that's where you can face some of those issues. Talking about the sand particle size or the size particle distribution, this is what we mean with that. You take just a regular sand sample, like the one that we saw that was wet, you dry that off, remove all the hydrocarbons, remove all the iron, if you saw some iron particles inside that, and you pass these through different sieves. The main purpose of that is try to identify the size of the particle that is going through. What we always recommend is you have to get multiple points to design the screen. So let me give you an analogy. If you take some sand sample, because you have a desander before, and you take a sand sample from the tailpipe, you have to take another sample from the pump. And if you can take another sample above the pump, and you're going to see that these 3 different samples, that is sand that it was coming from the same well, and you were expecting maybe to look the same, is going to be totally different. And the reason behind that is because the sand that you're collecting in the tailpipe, because you have a desander, is more the sand that has been capturing inside. The sand that goes through the pump and the sample that you're getting from there is sand that has been crushing with the stages when it's passing through in a high velocity and a high pressure. And the sand that is above the discharge of the pump is sand that already was crushing and is sand that now is flowing through the surface. So based on that, we analyze the sand that we're dealing. The best thing if you want to control sand that is going through your pump is getting the sample from the tailpipe, or just a portion of the frac sand that was or just the combination that it was used and the percentage, and you can now extrapolate this data. Again, this is dry sand, and now what you have to do is analyze a different correlation. Like this gray line that you see over here, we try to analyze the compactation, and it's more the sorting coefficient that you see on the particles, and based on the water cup and the oil viscosity and the API, we try to give a number just to see how much agglutination we're going to see just on the well, based on the samples that we're getting, based on how bigger it is and or how fine it is, the particles, and based on the viscosity that we're facing. So this is kind of like what we're going to see, and we're analyzing either if I can handle all of this sand just with one stage, or if actually I need an additional stage to handle the finer particles, or is I'm just going to give my ESP to leave the remainder of the sand that the screen couldn't filter. So that's kind of like part of the decision that we have to make based on the metallurgy that we're using on the pumps and the expectation that we're seeing in this particular field. Another thing that is important that people always ask is like, okay, but how many screens do we use? I mean, can we use just one screen, or do we have to get 2, 3, 4, 5? So there is always a combination between of the total fluid that you're lifting, is the well classification, and how do we take that is more on the amount of sand that you're going to lift on milligrams per liter. So there is a classification between average, bad, and severe, and what is going to cause is actually kind of like punish a little bit some of the numbers that we're seeing through. I believe there is more question. Okay, I think. So based on that, this classification and the opening that we're planning to use, the gap that we're using for that slot is going to determine the amount of open area. But at the same time, after you enter the total fluid that is passing through, it's going to give you a fluid velocity that is going through the screen. That velocity is calculated actually on how much fluid is passing through each small doors or rectangles that you have on the screen. And based on that, there is a design in handbook that is not recommended to exceed point based on the slot size and based on the opening on the screen and the tubing size. You get different numbers, but in this case, you cannot exceed 0.18 inches per second. What that means, if you exceed that number, it doesn't mean that you're totally just going to run your system. There is a point that because the wells are going to just get a peak and it come back, what they try to tell you is like, you cannot maintain that screen getting that high rate because your pressure drop is going to start increase. And now, if you don't have enough open area and the fluid rate that you were expecting is now keep increasing, you're going to get some jetty point, and that jetting point is going to start affecting the screen. Either if you're located in front of the perforation, you can start perforating the screen jacket and face some potential failures. So that's what they do. And you take this correlation based on the pressure drop that you're seeing through the screen. Again, after you determine the number of screens that you needed, and based on the open area, it goes all the factors. It tells you based on the water cup, API, viscosity, gravity, is going to calculate the pressure drop that you're facing through the entire design. This having consideration the 5 screen and the total length that you have per well. So what you want to do is be sure that you're analyzing the scale tendency, and you do that correlation to be sure at what point you can start creating some scale deposition. So you want to avoid that high pressure drop and being able to control and give enough open area through the system so you're able to produce. I believe there were more questions again. Oh no, it's for the attendance. The second stage, it goes back on the desander. Again, the desander is more recommended and based on the approach that you want, either to deal 100% of the sand or to deal with the remainder of the sand that the sand screens couldn't handle. So you're at least going to get another opportunity for the sand that has been already creating that coalescent effect, that it was in a paste and now it's breaking down in small particles, more independent particles, and it passed through the screen. Now you're giving another chance to knock out those particles due to a centrifugal force. The way that this works is not moving parts. They have just like a spiral or a helix that is connected at the bottom, and you have an inner tube that it goes on the inside. So fluid goes through the sand screen, falls down, but when it passes through that spiral or helix, it creates enough delta P that you're creating a vortex effect. This centrifugal force is going to help you to spin those particles that is still entraining the fluid, and you're going to force those to go back into the tailpipe or mud joints. Again, it will be based on the size of the particle and the angles of the helix, that either you can knock out 60%, 40%, 10%, 80% of the sand that passed already through the screen. And the way that you do that is based on the angle and the number of spiral that you have through. So that determination is going to be translated in more the amount of delta P that you're generating at this point. You're going either to increase or decrease the acceleration of the particles, being able to knock those particles through the wall and have a better separation. There is always a balance. If you increase too much that centrifugal force because you want to face or you want to push 100% of that, you can generate enough centrifugal force that you can actually sandblast the tubing, and you can now have a jetting effect at this point and actually cut that out and have a efficient job. So there is always a balance based on the rate and the total sand that you're producing. So we measure that out and we kind of like give you a recommendation and go with you guys through the process of how this should be sized. And we're going to talk about that in a while. So again, if you just go with the regular desander, like I mentioned before, you have like a 2 or 3 or 5 wider slots that's based on the provider. But what you're doing is just having all the sand that was coming from the wellbore, and it's more like a vacuum. It just goes inside and just either you're spinning a portion of that sand, filling the tailpipe, and now fluid will go through the inner tube. Some of the issues that some operators face on the past is, like we discussed from the beginning, if I don't have enough flow back and I'm putting my ESP at day one to live with all the sand, sometimes it's how fast can I actually fill those mud joints or tailpipe. Some people have been filling those out in 8 days. Some people it's taking more than a year and a half. And the secret or the point behind that is how we're operating the well and how much sand we're actually regulating and the rate that I allow that ESP to produce the sand. If we're just depending on a desander or the sand screens to do 100% of the job, we can fill these out in hours. And that's why we have to more regulate that sand that is coming back to allow us to leave that out without causing high damage into your pump and being able to provide the right ratio. So that's the main key factor over these designs. I'm just going to show you a video of how that vortex or centrifugal force works and how you're able to pull some of that sand into the tailpipe. So over here, we can see kind of like a combination, the one that we discussed, the sand screen with the spiral underneath it. So we see fluid going through the screen, and when it's coming down based on the spiral and the angle, you're going to generate that force. This doesn't move, it's just the force that you're causing, creating that tortuous path around the helix, and this is going to spin out and generate that centrifugal force. What I was meaning early before, if I don't do the right calculation based on the sand volume or sand rate and the fluid production, now my delta P is going to be too high that I can push this force 3 feet, 4 feet, 5 feet underneath it, and that amount of sand hammering constant the ID of the tubing is going to start to creating some mark and start sandblasting the internal factors or the internal components. That's what I have to have all those factors in consideration when I do my design, so I'm able to control this out and be able to return just fluid with less portion of sand or clean fluid through my pump, so that I'm able to actually handle the sand what I'm doing here and what we always recommend is less delay the process. Once again, instead of dealing with all the sand at once, let's delay that process and break those 300 pounds, 200 pounds, whatever it is. Let's break it down to the point that my ESP or rod pump can produce it without causing damaging through my system. So again, it goes back to extending runtime, longer time production, increasing the production rate, and help the economics. That's where you see the differential factor, is being able to, instead of pulling this well once a year or 3 times per year, is move that needle and be able to actually go one every year, or some cases where they just go from one ESP immediately to rod pump, because you're able to keep this well and hold for actually like a year and a half or 2 years, to the point that now the failure is more because you have an oversized ESP and it's too big a pump for the amount of ratio that is passing through. So just to summarize everything, it comes back to the operation efficiency and the parameters. It goes on the design of the desander, if you're planning to use that, the helix and the angle that you're choosing, and the length of the screen or the sand control management system that you're planning to incorporate. The material, what I mean material is the metallurgic that you want to use, either boronized, either you want to use just regular carbon steel, stainless steel, and the type of intake is either you want to use an slotted intake or a screen intake. The fluid properties, that's something that please have in consideration. Lighter oil API like 40, 42 is not the same that dealing with 10 API oil. The viscosity is going to be different. The way that the same particle that maybe is 100 mesh or 2040 is going to behave different in every single well due to the viscosity. Sometimes you don't have to have a tighter screen to be able to filter those finer particles, because those finer particles are becoming more chunks and is bigger due to the viscosity of the fluid, that it maybe can go with a wider opening and being able to have the same effect of sand management without causing a premature failure. I think there is, different thing from the chat. The production parameters, we always go back either with the pumping speed or with the frequency, if that is ESP or rod pump. You cannot relate 100% on the desander to do their job. There is a combination, and we're going to see that one in more detail when we talk about gas separation. There is always an integral system, and we need to analyze the stroke length, pumping speed, pump spacing. We don't want to tag the pump, but at the same time, you don't want to have a wider spacing that it can affect your runtime or your pump efficiency. The fluid rate that is passing through and the PIP, those are factors that, again, when you increase the drawdown, it's fluid that is coming through, but it's sand as well that it goes through if you're facing or you're dealing with a sandy well operation. And sometimes, you know, we got to the point that we analyze everything, and they are maybe assuming that it's sand. We do the solid report, and that's why we have that sand sieve. And in reality, maybe it was not just sand. When we see what was plugging the standing valve or your plunger or your ESP, is more iron sulfide. And people is kind of like, because they see kind of like chunks, they say, oh no, that's maybe just sand because this is a sandy well. In reality, maybe it's not sand what is causing the problem. It's just that iron sulfide that now is affecting my system. And maybe just with enough and the right chemical, I can treat the well and eliminate that iron sulfide that is causing this type of premature issues on my stages or my plunger. So the question that we get all the time, what about efficiency? What is the efficiency that I can get for each of the helix or desander? Or can one spiral deal with 5,000 barrels and come back to zero? Mohammed, I guess you have a question. Mohammed Salat. Are you there, Mohammed? Mohammed, can you talk now?
Can you hear me, sir?
Yes, I can.
Okay, can I ask questions about this diagram or graph? Helix 2, 3.
Can you repeat that one again? You was cutting in and out. Sorry.
What?
Can you repeat it? You was cutting in and out. The internet signal was not good enough, so you was cutting. Can you repeat your question?
Okay. My question, what is the reason for this dramatic increase in this graph or profile? The first profile?
So is I'm understanding your question correctly? Like, what's the reason of this graph related with this spike? Is that your question? Mohammed, are you there? Is that your question? Like, what is the reason between the graph, or what is the relationship between the graph and the helix?
I ask about increase in graph and the relation between the first graph and second graph.
But are you referring those two graphs, the ones that I'm seeing in this slide between helix 2.3 and 2.4? What is the relationship, or the ones before are the ones that you're referring to?
I can't tell.
It's because the signal is a little bad, but if I understood your question correct, and let's assume that that's your question, and if not, please, I apologize and ask again. But if your question is what is the difference between those two graphs, it's more worth showing over here different helices. So that means the angle is going to differ between this one and this one, and how much delta P and how much fluid velocity I'm going to generate based on the type of sand that I'm dealing with. So if we go back over here, what we did a study where we was dumping multiple sizes of sand, and based on the different rates, we see kind of like a correlation, like based on the angle and the spirals that I have through, some were better generating centrifugal force at a particular rate and give me a better efficiency to control the sand. So like this one, 2.3 helix, the ranges for operational, or the recommended ranges, like in the case, it could be, let's say 300 to 450. That's the optimal range. It doesn't mean it's not going to work for any higher or lower rate. What it means, you become to the point, if you overpass these and it's always operating at 1,000 barrels per day or 800 barrels per day, the range is too big and you're generating too much force that you can cut the housing based on the type of particles against that you're facing through. If you maybe go with just 100 mesh, and sometimes that's good, and we want to create that additional force kind of like on purpose to generate and push some of the solids through the tailpipe. So every single angle, like the 2.4, what it's doing is, again, a similar correlation and give you the efficiency based on the ranges and the particles that you're lifting. But it becomes the point, if we design a well that was for 1,000 barrels and it came back to 100, it doesn't mean it's not going to work. It will work, but the efficiency after time, because you're changing the total fluid that was passing through, the delta P is going to change. Your efficiency is going to start declining slowly. And that's why we always use this in correlation with rod pump, because every time that we change either the pumping unit from a conventional to a Rotaflex or any hydraulic system, where we increase that stroke length from, instead of being 198 to 320, because maybe we have gas as well and we want to get, longer stroke to deal with the gas and lower pumping speed, that's great. But that delta P is changing at the bottom, and we have to be sure we give the right helix and we get the right force to be able to spin those solids and spin those particles out and generate that filtration or separation that the customer was looking for. So that's why all those graphs, all those correlation goes back with the jarring area and the Baines angle that I got on my system. I want to be sure when the fluid pass through, I generate enough delta P that is going to give me that acceleration to allow those particles to spin out and actually being able to be into the tailpipe. If this angle is too big and my delta P is not enough, the fluid with the sand, when it passes through, it will not generate enough centrifugal force, and that sand will remain in solution, and it will go through the pump, or it will fall back and it will go straight inside the inner tube. And at that point, your efficiency is going to be super low. Either you don't do any filtration, and those are some of the cases that we hear from people saying, hey, I have a desander, the desander, I pull the well, there is no sand in the tailpipe, but I get all my pump totally destroyed with sand. And you kind of like open the desander and you don't see any erosion, any marks that actually you was spinning those particles out. You will just see that the sand just bypassed the system and it just went through. And sometimes has to do just with the angle. Maybe the helix was not the right helix. Maybe the operational conditions were different to the ones that it was originally designed for. And those cases, you're going to change the delta P and you're changing that acceleration and that force. So again, this one is to give you kind of like a better view of what I was talking about with the different angles. And all the fluid that is passing through have to follow this angle, have to go through this. And that's what you're creating that acceleration and you're creating that vortex. Either this vortex is too weak or is too strong, and that's how you're able to filter the sand. When this is strong, you're able to have those particles hitting this wall. And after that, the centrifugal force or the wave become with a lower delta P and a lower spin, that the particle will just fall back into the tailpipe or fall down through the tailpipe. What you want to do is wash the amount of force that you are implying through the system, so you don't have too many red points and you're able to keep this in the right ratio so fluid can come back and sand, just a portion of that will fall into the tailpipe, the remainder will just go into the inner tube. So that's what we do, analyzing all those conditions. That's what there is different helices sizes, there is different ranges. Normally on the catalog or brochure for any desander company or company that provide this desander, they give you ranges, but those ranges is more kind of like a particular choice that you can get in standard condition. If you really want to deal with a more problematic well and you want to analyze case by case, go back with the service company that you're buying this from and ask them, you know, I want to be sure this is the pumping unit that I have, this is all the conditions, so we can improve that efficiency. There was another question from Admit. I believe it's this Admit. Yes, sir. Do you have any question, Admit? Hello?
Yeah, hello, sir. Thank you for your good presentation. And my question is about the helix size, but you clear it, so thank you.
Okay, perfect. I'm glad that I was able to answer. So again, this is kind of like the generic chart. There is always, you can go and drill down and do more simulation of how much force is actually created. That's why the length of the tools, we always come back to almost the same point, like we have been discussing. The sand rate is going to determine part of the erosion. The type of helix is going to give me that acceleration, and it's going to determine the wave of that vortex effect and the distance that I can displace that out based on the delta P that I have as my intake or my enter point for the fluid. And one of the things that you want to do is keep the delta P or keep that wave or the vortex effect inside the body of the descender, because normally those bodies are thicker and you get a special metallurgy in those to be able to handle that erosion that you're facing. If you don't do that, that's where you can potentially have some issue. So we give you some calculations of how you can determine that sand penetration rate when it goes through the metal. So you kind of like have in consideration the sand velocity, the ratio of the pi, the type of metallurgy you're using, and what you want to come back to a conclusion is either with this rate, how fast I can actually destroy that housing, or that velocity that I'm having through and that vortex effect is going to be the right ranges so I don't create an additional problem and enable to control that vortex effect. So this will give you kind of like a better picture. This is what we call low penetration. So normally any descender, when it's doing his job, you will see these marks. And at this point, it will mean, regardless for this material that it was a stainless steel, you get the right helix, but again, in one point, either the pressure increase or the drawdown increase, and you start to create a mark through the system, or the sand rate increase, and that's what you see this. Remember, you don't have just sand. We always get a problem with corrosion as well. So after you expose that portion of the metal, corrosion can go back and start attacking and create a weak section for that steel. So it can cause on the future a high penetration rate, where either due to the delta P or the drawdown, now you're eating that metal. And it's funny, you're always going to see kind of like this vortex effect, and those marks is going to follow the same angle or the same pattern of the helix that you choose, because this is how you're causing that displacement. So the problem with that is we don't do a good job dealing with the sand, and we don't do a good job sizing. This can happen that you actually cut that housing or cut that descender. That's why you need to be sure, or if the force is too high, like this picture, and the operator actually cut the first tailpipe joint that was below the descender. That means that helix was too small, and it kind of like create too much acceleration that it was able to travel more than 4 feet, and that high erosion start happening at this point. And that tailpipe is not normally designed to handle erosion, so it becomes a weak spot. When you do a good job sizing and the well lasts 2-3 years or whatever was the runtime, and based on the ratio and everything, you will see just the marks inside that housing without trespassing the body. You will see kind of like what happened in a high rate and a lower rate, and it slowly start coming up. So conclusion for just the metallurgics or the different materials that you can use on those housing, you can use just carbon steel, you can use plastic coated, that's more related due to corrosion. You can use nickel plated, and again, it goes more to a moderate high corrosion. You can use stainless steel, it's more for corrosion. The problem with stainless steel is going to be soft, so you're going to see maybe more erosion damage. And the special alloy that is part of the boronite, you can see more resistant for corrosion and erosion, because it's metallurgic that is designed for those type of environments. So this just to show you what we were talking about. When you get the boronite, you don't see any marks. I mean, they do an amazing job controlling that force and controlling that erosion, that because it's an infused bottom that it goes around the metal, you're going to be able to see no affectation through it and no concerns about fishing job. The problem when you don't have the right ranges or you don't design this, that's less than 1 year and now you're paying for a fishing job, and that's what your cost can go up. So we talk about the design of, or the type of intake that I can have, and there is always a relationship also between that efficiency. We already talked about the efficiency just for the descender, but when I choose different intake, we're going to see that the reason that you maybe will see a higher rate when you use the screen or a higher efficiency is because now you're regulating more the fluid velocity that pass through. You are able to break those chunks of sand before it goes through the helix, and you are creating a better laminar flow that is going to generate a better acceleration of the particles for 20 feet or whatever will be your design, and you're able to actually baffle in that sand and control that one before it passed through the vortex. And at this point, you're dealing with a better homogenized fluid and sand. And then when you're dealing just with a traditional desander, you don't see that effect. It's just a big enter point where there is no regulation. It's just all the sand goes at once. At least with the screen, you're able to actually select how much sand you want to reject and what is the particle or what is the ranges that you're going to allow that sand to come inside the system as soon as it's smaller than 180 microns or 200 microns. It will be based on the design that you guys are approaching, and that's what is going to keep your efficiency for that sand management. Again, just talking about the same concept, the pumping speed. In case on ESP, you're going to see it's more on frequency. So the velocity and the drawdown that you're generating, that velocity is going to determine based on the helix, based on the parameters, based on the conditions, it's going to help you to keep an efficiency between a particular range, either 75, 85, 90. You're going to see those changes once you start depleting this well and you start changing operational conditions. Same thing in case that it will be a rod pump. That's what we always talk about, the appropriate helix for the right ranges. You don't want to be oversized. You want to keep on the right parameters so you're able to get standard conditions. Again, I like to bring these pictures just to keep everything in mind. We talk about sand that has been regulated, that has been breaking down, and it's because this is what we're dealing with. This is our challenges. It's more bigger particles, bigger chunk that has been agglutinated. Maybe people that is watching us today and is in other countries like and are facing with heavy oil or steam flow, they has been seeing in those tear down how the sand actually agglutinate and it can affect the system, or on the other hand, how the sand could be so loose that it could now create a different type of problem. So viscosity, the helix angle for the descenders, whatever you guys are using, is going to come back to the point of efficiency. And that's why you want to be sure you ask your supplier for the right ranges and the right approach so you can analyze what exactly do you need for each particular well. And if you actually have to have a screen, or you can handle without the screen based on the problematic that you're facing and the type of sand that you're dealing with. So again, this goes kind of like back and forth. Now, just dealing with the traditional descenders and the benefit that we can see and some of the optimization that we can get into the pump. I like to show this kind of like before we finish is we talk about upgrading equipment on ESP. There is an upgrading equipment or non-API pumps that you can use for sandy wells. There is a Harbison-Fisher Sand Pro, or Weatherford, they call this Sand Hot. There is a Pampa pump, a Weatherford called Sandy pump. So just to show you the list, there are some non-API pump, there are some non-API plungers that it can help you to improve some of the sand management. There is like what they used to be called lubri plunger. There is now chemical that is microencapsulated, that is more lubricant, that it help you to reduce that sticky plunger. The desander that we talk about, there is different discharge, there is different extension wiper that you can have to the system just to improve that sand rate. It's not going to be just one solution for all the wells, but it's alternative that you can add to complement that out. There was something that we mentioned over here, and it's more the clearance based on the type of sand management system that you decide to use. You don't have to go too big or too small in your clearance, because sometimes when you go like 8,000 of an inch. Now you're creating an slippage that on the future, what is going to cause is actually you're losing maybe 1 barrel per day or maybe 2 barrels per day. We can do the calculation based on the fluid conditions. Sometimes you actually need that clearance based on the viscosity or based on the amount of sand that you're allowed to pass through. So that's why the sand sieve particle site distribution or the sand sieve report is going to help you to understand what is the sand that is actually passing around. So just keep that one in mind. That is always looking the entire system. This is the sand flush plunger I see customer using or sand diverter from down end, customer using with great success rate. But again, it doesn't mean this is your sand control system. This is just a management system. It's something that is going to help you to extend the runtime and help whatever approach you use underneath the pump. This is just an additional resource that you can take to improve that production and improve that that approach. That's what we got for session number 1, that is sand control management. I don't know if there is any questions or additional things. I know we almost run out of time. We kind of like extend 10 minutes more, but we're open to answer any question or anything that maybe anybody has. I don't know how it's going to be the dynamic. Are you guys setting a Q&A or? Okay, if there is no questions, thank you. Thank you everybody for your time, and I hope you guys enjoy it. And you can find, I will text my email. So in case that there is anything, feel free to email us or ask anything. We're always open to have phone conversations and help you as much as we can.
So, thank you, Engineer Gustavo, for this session. And we are willing to see you in good health in the 18th of August session, inshallah.
Yes, sir. No, thank you. We'll be having the gas management session ready.
Thank you very much.